Yes. Okay. Thank you very much. It's a pleasure to be talking here. So I'll tell you today about some recent work on the resurgent structure of topological string theory and some remarkable connection to L functions and quantum modular forms. And this talk is based on a paper of mine from the end of 2022, and very recently 2 follow-ups with my collaborator, Veronica Fantini. So okay, we have a technical problem. Okay, sorry. So I'll start right away with some motivations. Okay, more problems. Maybe you can read this better. So you probably all are very familiar with how resurgence appears in quantum theories and how the machinery of resurgence applied to this factorially divergent asymptotic series produces generally a collection of complex numbers known as Stokes constants that give us crucial information about the non-perturbative completions to the original perturbative expansions. Now, these Stokes constants are generically complex numbers, yet in some very remarkable cases, they turn out to be rational numbers or even integer numbers, and to have even if conjectural, an interpretation in terms of enumerative invariance. For example, based on the counting of BPS states. Now, here I list a very incomplete series of works where this has been found to be true. So we have n equals 2 4-dimensional super Young-Mills theory, complex Chern-Simons theory, and more importantly for this talk, the case of topological string theory, where more or less all types of theories like standard, Nekrasov-Shatashvili, the refined topological string, on-toric, and also non-toric Calabi-Yau trefoils have been studied. In particular, I will focus on the case of the standard and Nekrasov-Shatashvili topological strings on toric CY trefolds. So very quickly, I'll just take 5 minutes to recall some basic notions in resurgence that you're all very familiar with, but I want to set the notation. And so let's just take phi of Z be a simple resurgent Gevrey-1 asymptotic series where the ANs are complex coefficients. So they have this factorial type divergence. Now, the Borel-Laplace resummation along a generic direction theta in the complex plane is the sequence of 2 processes. So we have, first we take the Borel transform of phi of Z, which means we factor out the factorial divergence from the coefficients. And we obtain this locally analytic function at the origin with the generic pattern of singularities that I denote by zeta omega. And then if we apply the Laplace transform when this is possible along the direction theta, we obtain this S theta phi of Z, which is now locally analytic in the complex Z plane, but it inherits the structure of singularities of the Borel transform, meaning it has discontinuous jumps at the rays that are identified by the singularities of the Borel transform. I'm interested in the case where the Borel transform has only either logarithmic branch points or simple poles. And so in this case, let's take the case of the logarithmic branch point. If we expand the Borel transform at the singularity zeta equal to zeta omega, we have the expected logarithmic type divergence times a perturbative part, the phi at omega, at zeta minus zeta omega, which is the germ of an analytic function at the singularity zeta omega. And then I factor out this complex number S omega, which is the corresponding Stokes constant. Also, I call Stokes rate the line rho theta that is identified by the angle determined by the singularity zeta omega for any zeta omega. Okay, then given these tools, one of the most natural things to do are computing the discontinuity and the median resummation of the original asymptotic series across any Stokes ray on the complex Borel plane. Now, the discontinuity is just the difference of the two lateral Borel Laplace resummations, going slightly above and slightly below the Stokes ray. And this, just applying a standard contour deformation argument in the complex plane, it can be written as this sum over the singularities of the Stokes constant times the exponential type non-analytic contribution at the singularity times the lateral Borel resummation. And the median resummation is just the average of the two lateral Borel Laplace resummations. Now, this procedure that I have described very quickly can be schematically reproduced with starting with all of the asymptotic series that are obtained in this way. And so we started with phi, obtained this collection of asymptotic series phi omega and Stokes constants S omega. And from this, again, from every phi omega, we can produce a new collection of asymptotic series and Stokes constants. Now, it's useful, helpful to introduce the notion of a basic trans series. It's just a notation to put together the exponential and the perturbative contributions at each singularity zeta omega, this phi capital omega of z. And now, if we consider the lateral Borel Laplace resummations as operators acting on the basic trans series, then we can define the Stokes automorphism at the angle theta by the composition. And finally, the last notion I want to recall about this is the one of minimal resurgent structure, meaning that I will call minimal resurgent structure the smallest subset of basic trans series that are built out of the original asymptotic series phi, and that are closed under the action of the Stokes automorphism. Now, at the same time, once we have defined this subset omega bar of all the singularities that identifies the basic trans series in the minimal resurgent structure, then we can also introduce the corresponding matrix of Stokes constants, S phi. Okay, so this is all that I wanted to recall very quickly. And so let me get into the proper topic of the talk. And so I want to apply resurgence to the context of, as I told you, topological string theory on local CY threefolds, but more specifically, within the so-called topological string spectral theory correspondence. That is a way of identifying the topological string on local CY threefold with the spectral theory of some appropriately constructed quantum operators on the Calabi-Yau. So let X be a generic toric Calabi-Yau threefold. So by mirror symmetry, we know X is paired with an algebraic curve sigma in C star times C star, and I denote by G sigma its genus. Now, the standard Weil quantization prescription allows us to build a collection of quantum mechanical operators rho J. So there's as many as the genus of the curve, and this act on L2R. These are conjectured to be positive definite and of trace class under some light assumptions. And this is proven in some examples, and in all examples I'll describe later on. Then one can always compute their generalized Fredholm determinant. So this is a way of constructing one unique determinant out of the collection of these quantum mechanical operators. And this is an entire function of the complex deformation parameters of the mirror out of Cy, which I denote by kappa j. J again goes from 1 to G sigma. And by locally expanding this Fredholm determinant at the orbifold point in the moduli space of the Calabi-Yau, we obtain a collection of analytic functions zeta that appear as coefficient functions in this expansion in kappa. And these are called the fermionic spectral traces of the Calabi-Yau. These are functions of this vector n of integers that kind of take the place of the complex deformation parameters of the Cy. Then psi are again the mass parameters. We can just ignore them. And h bar is the a quantum deformation parameter that is introduced with the quantization procedure and plays the role of the Planck constant. Now, these are originally just analytic function of h bar in R positive, but we can assume that we can, well, we assume that we can extend, analytically continue these spectral traces to the whole complex plane in h bar minus the negative reals. And again, we can verify this explicitly in all examples. Okay, now this was one side of the correspondence, if you want, the spectral theory side. Now, to give you the complete picture, I need to introduce also the relevant quantities in the topological string side of the correspondence. And we really only need to introduce what the total ground potential of the topological string on X is. So this is the sum of two contributions that are called the worldsheet and WKB ground potentials. And this, if you want, they identify the contributions from the standard and the Nekrasov-Saakashvili topological string partition functions, respectively. And in particular, the WS, the worldsheet ground potential, is determined by the Gopakumar-Vafa total free energy after the B field has been turned on, and the WKB ground potential instead is related to the derivatives of the Nekrasov-Saakashvili total free energy. Okay, then the statement of the TSST correspondence is very concrete, and it tells us that the fermionic spectral traces that I've introduced in the previous slide are given by an integral transform applied to the total ground potential of the topological string theory on the Calabi-Yau. And here, the mu's are just related to the complex deformation parameters by taking the logarithm. And importantly, also, the statement of the TSST correspondence comes equipped with a strong weak duality in the couplings, meaning that the standard coupling constant of the topological string GS is given by 4 pi squared over the quantum parameter h bar. And so this is the setup. And if you don't have questions on this, then I'll move to describe what is a conjectural proposition on the resurgence of these fermionic spectral traces. So if we fix n and we consider the logarithm of the fermionic spectral traces, and we take the limits for h bar going to 0 and h bar going to infinity, then we naturally construct two different asymptotic series that are simple, resurgent, Gevrey-1. And then, of course, we can apply resurgence to either one of them. And we can, in particular, observe that the resurgence of this asymptotic series always seems to respect some properties. And so we describe this conjectural proposal on the resurgent structures. Let me just quickly tell you about the limit h bar going to 0, and then the dual limit will be almost analogous. So we observe in examples and conjecture in general that this minimal resurgent structure contains basic trend series of the form I write here. So this capital phi of h bar depends on two additional indices, the small n, which is any integer, and then the sigma, which takes only finite a set of values from 0 to L0. And then A0 is a complex constant. Here, L0 and A0 are determined by the geometry of the Calabi-Yau. And so what is this conjecture telling us? So what we observe in the example is that in the complex Borel plane, the singularities, which are always these logarithmic branch points, appear to be distributed on only a finite number of vertical lines, which are counted by this index sigma from 0 to L0. And on each of these vertical lines, the singularities are repeated at the integer multiples of some fundamental constant, which is the A0. And the index small n is exactly counting the position along the individual tower. And okay, so also importantly, as you notice from the formula for the basic trend series, once you fix the tower, the perturbative contribution at each of the singularities along that tower is the same, as it only depends on the index sigma. And the exponential contribution instead, the exponential type factor e to the minus n A0 over h bar, does not depend on the tower. A0 is some constant that we observe to differ from Cy to Cy, but to be no. So we don't. So we can't really describe the way L0 and A0 depend on the geometry, but we observe that, yeah, fixing the geometry fixes it, and we observe different ones for different Cy's. And so this is exactly what has been described in the literature as a peacock pattern. And so this is also observed in Chern-Simons theory on the complement of hyperbolic knots, for example. And now we also observe that the corresponding infinite dimensional matrix of Stokes constants is such that well, all the entries are rational numbers. So the Stokes constants are rational numbers after fixing, of course, an appropriate normalization of the perturbative series. And we can naturally organize this Stokes constants into Q series. So we write this as sigma sigma first as this series over n of the Stokes constant times Q to the n. Which are the generating functions, and the examples, we're always able to write this Q series in closed form in terms of Q Pochamer symbols. The tower. Yeah, exactly. And this structure that I've described, that we conjecture in general for the semi-classical limit h bar going to 0, then we also observe analogously in the double regime, where now h bar goes to infinity, or if you want, GS goes to 0. And so we have, again, this minimal resurgent structure of basic trend series, where you have now a different constant A infinity that determines the step distancing the singularities along an individual tower. And a new collection of Stokes constants, again, in Q, which I denote by the letter R. And so the schematics of this conjecture is that we observe peacock patterns in the complex Borel plane for both limits, h bar going to 0 and infinity, and the corresponding infinitely many Stokes constants are rational, and they seem to be very closely related to integer invariance of the geometry, even if, as I will describe more in the following, we don't have a very explicit geometric and physical understanding of these integer numbers. Yes, so I will tell you. So in the examples, we find that there is, so they're not just any rational numbers, they're very special rational numbers. And so they're very easily related to integer sequences. So for example, in the case of the local P2, where everything is explicitly and exactly solved, then the Stokes constants are, and so the end Stokes constant on a tower is an integer number over n, and so we can easily build an integer sequence out of that. So for the rest of this talk, I'm gonna focus on the case of local P2, where a lot is known, everything is known really. And this is because we've been able to solve these resurgent structures exactly. So local P2 is the benchmark examples of toric CY trifolds. And it is the total space of the canonical bundle over the projective surface. So here I show the toric diagram of the geometry. So this has no mass parameters, and it has only one complex deformation parameters, being a genus 1 geometry. And this is so it's a toric Del Pezzo CY trifold in particular. So applying the Weyl quantization to the mirror curve gives this quantum operator OP2 in the exponentiated operators e to the x and e to the y acting on L2R. And this, now if we take the inverse operator of this, so rho is equal to O inverse, then this is shown to be positive, definite, and trace class. And so this is the standard construction in the TSST correspondence that I've mentioned at the beginning. And now we can consider the first fermionic spectral trace, that is simply the spectral trace of this operator rho. So we only have one. And importantly, this trace has been computed explicitly by the people I cite here. And it shows an explicit factorization into holomorphic and anti-holomorphic blocks. So it has this factorized formula where now these objects are the Q-Pochamer symbols. And in particular, B squared is related to H bar as 2 pi B squared is equal to 3 H bar, and Q tilde are the usual exponentiated variables in B squared and 1 over B squared. And W is simply a constant. Now, because we have this explicit formula for the spectral trace, then we're able to say a lot about the resurgence of this object. In particular, we can compute, first we take the logarithm of the trace because it makes computations more accessible and the properties of this object more accessible. Then we can compute the all orders perturbative expansions at both weak and strong coupling in H bar. And this gives us two Gevrey-1 asymptotic series that are phi of H bar and psi of tau. Here, tau is simply given by the inverse of H bar. And here, these coefficients A2n and B2n are known in closed form. I haven't written them here, but they're simple functions of Bernoulli polynomials and factorials. And given that we have these coefficients in closed form, then we can obtain the exact resurgent structures of these Gevrey-1 series. So the first step is that using the Adamard multiplication theory, we can obtain explicit resummations of the Borel transform. So the phi at zeta and psi at zeta are known analytically, and are simple resurgent functions as expected. In particular, they only possess logarithmic branch points, and these occur on just one tower that is located along the imaginary axis. And so they are separated at these integer multiples of the constants a0 and a infinity. And now if we take the local expansions of the Borel transforms at the singularities, in both cases, we obtain a very simple structure that is, as you can see in this formula, there is no perturbative component attached to the logarithmic type divergence. There's only the Stokes constants. So we have this Sn and Rn are the two Stokes constants that weaken strong coupling, and we obtain them exactly in closed form. So thanks to this, we can prove a whole series of number theoretic statements on this Stokes constants, their generating functions, and their Dirichlet series. So let me start with the first step, that is, once we normalize the Stokes constants by the first S1 and R1, then we prove that they are some relatively simple arithmetic functions. They are divisor sum functions. And in this formula, chi32D is the non-principal Dirichlet character modulo 3. And observe the arithmetic duality that relates them as the factor that multiplies the Dirichlet character is D and N over D. So we're just exchanging the two dual arithmetic divisors. These are, of course, multiplicative arithmetic functions, and they have two very elementary properties like the even and odd parities. And here you see the two towers in the Borel plane, and attached to them are those integer numbers that I mentioned before. So we just take this sequence of rational numbers and we multiply them by the index n. This defines a sequence of integers that, as I'll show in a moment, appear to capture a lot of the geometry of the problem. So I'm gonna describe now a sequence of properties, and then I'm gonna try and put them together, giving you the global picture of what is happening. So the Stokes constants are generated by Q tilde series. And this Q tilde series can be written in closed form. And then we can observe that they're exactly the same anti-holomorphic and holomorphic blocks that appear in the decomposition of the spectral trace. So those blocks that appear in the factorization formula I showed before now come back as generating functions of the Stokes constants. But interestingly, note that the two holomorphic and anti-holomorphic blocks that are the ones that produce the asymptotic series phi of h bar and psi of tau at weak and strong coupling, then they also give the generating functions of the Stokes constants in the opposite regime. So here you see, for example, the discontinuity of phi of h bar is given by the anti-holomorphic block, the one in Q tilde, which is the one that gives the perturbative expansion at strong coupling, that is the psi of tau, and vice versa. And this exchange of perturbative and non-perturbative contributions is something that keeps appearing in this story, and I will later try to explain it more carefully. Then there is, in some sense, also a dual statement, that is that one proves that the perturbative coefficients in the two regimes are given by the Mellin transform of the corresponding discontinuities, as I write here. And this tells us that the perturbative expansion of one block can be obtained directly from the dual block by means of these two statements. Now there's another pair of statements that I want to make. Again, these are all proven, starting from the exact expressions for the Stokes constants. And that is the perturbative coefficients of the asymptotic series in the two regimes can be written in terms of two Dirichlet series evaluated at even and odd integers. And these are exactly the Dirichlet series that are built out of the Stokes constants. So these formulae here for the A2n and B2n, they are obtained from the so-called large order relations once all of the contributions are taken care of. And so these asymptotic relations are made exact. And now one can start investigating this Dirichlet series and wondering what their properties are. And the first and most important thing to say is that the Dirichlet series that are built out of the Stokes constants can actually be analytically continued to L functions. So they satisfy an Euler product expansion, and they are convergent in some right half plane, and they can be analytically continued to the rest of the complex plane. And so these L functions are also deeply related to each other as they admit this factorization. You see the L function that describes the weak coupling factorizes into the product of, so the first term is the Dirichlet L function that is associated with the character chi32. And the second factor is just the Riemann zeta function. Now the same factorization also applies to the L function that is identified by the strong coupling. However, there is this symmetric shift by 1 unit in the arguments of the factors. And so putting these 4 statements together into one global picture allows us to understand that something quite deep is happening, as really the exchange of perturbative and non-perturbative content between the dual regimes can be expressed in a mathematically precise way. So we introduce this strong-weak resurgent symmetry in the work with Veronica. And what we mean by this is that the resurgent structures at weak and strong coupling embed into this global construction, as they in particular give a commutative diagram where each vertex allows us to reconstruct the whole diagram. And so in particular, the content of each vertex is equivalent to the information contained in all others. And so this diagram puts together all the information that I've described so far. And what it's telling us is that, so if you look at the top 2 vertices, then you have the discontinuity of the series at strong coupling. Now, if we take the expansion as h bar goes to 0, we get the perturbative expansion phi of h bar. Then we can apply resurgence as I've described, and we get this collection of Stokes constants and singularities, this tower of singularities. And then out of this, we can either construct the generating series that gives us back the discontinuity of the asymptotic series, or the Dirichlet series that gives us this L function L0. A0 is just the fundamental constant separating the singularities in the Borel plane. And I've also told you that there are these two-headed arrows connecting the L function directly with the 5H bar and its discontinuity by means of the exact large order relations and the Mellin and inverse Mellin. And then we can, of course, also describe the same way the other half of the diagram. And so putting everything together, this is what we call the strong-weak resurgent symmetry. And so this fundamentally, we can boil it down to the interplay of the Stokes constants with its generating functions in the form of Q series and their L functions. And so these very basic ingredients can also be investigated independently of all the setup. I've started with the one of topological strings, and this is what we do in the other paper with Veronica when we talk about modular resurgence and modular resurgent structures, and I'll try to briefly mention them at the end of the talk. But I also want to point out how this structure that we have observed, once we take a step back and we think about the topological string spectral theory correspondence again, is hinting at the fact that somehow both regimes in H bar are so the two regimes in H bar are not independent of each other, but they are completely determined one from the other. And so at the level of the topological strings, what we are saying is that there is a potentially mathematically precise way of connecting the perturbative and non-perturbative contributions to the standard in Nekrasov-Shatashvili total free energy. That is what, according to the DSST, enters the game in this spectral traces that I've described. Even if this is work in progress, like understanding this more precisely. Now, we can add some other steps to this process as one can realize that this normalized Stokes constants are actually related by an arithmetic twist. So this is something one can prove using the divisor sum formulae. And so we obtain the weak coupling Stokes constants by applying this specific twist that comes from the same Dirichlet character chi32 to the Stokes constants at strong coupling. And now this statement at the level of the Stokes constants translates in the language of the L functions as once we complete the L functions by adding the gamma factors as it is usually done in number theory, then actually these completed L functions satisfy a functional equation, which is that lambda 0 of S is equal to lambda infinity of minus S, which tells us that when considering the L functions in the whole complex plane, then the analytic continuation of the L function at weak coupling is given by the L function at strong coupling and vice versa. So if you want, again, these two statements can be introduced in the commutative diagram before us to horizontal arrows that join the Stokes directly or the L functions directly. This somehow completes the picture. And but then it suggests a new approach to these resurgent structures that satisfy the same fundamental properties of the trace of local P2. And so this research has brought us to the definition of modular resurgent structures. So let me first tell you about the connection to quantum modularity, and then I'll give the general definition of modular resurgent structures. So I just want to quickly recall the notion of holomorphic quantum modular forms. So let f be any function on the upper half plane. Omega, the weight, is either an integer or half integer. Then we say f is a holomorphic quantum modular form for a subgroup in SL2Z. If the cocycle H gamma f of y, that is this failure of modularity, where gamma is any element of the group, is holomorphic in this set C gamma. So these are all the points in the complex plane that satisfies this property. Cy plus d is not negative real. So this is a definition given by Zaghir in 2020. And I wanted to recall it because once we look at the generating series of the Stokes constants at weak and strong coupling, but we forget for a moment the specifics of the problem. So imagine you're just given these sequences of rational numbers, Sn and Rn, you build their generating functions. Then this f0 of y and f infinity of y define periodic holomorphic functions on the upper half plane. And then we can prove that these generating functions, f0 and f infinity, are holomorphic quantum modular forms. And in particular, they have weight 0, so we call them holomorphic quantum modular functions. And they are so with respect to the congruent subgroup gamma 1, 3 in SL2Z. So first of all, you see that if we just apply a change variable from y to either h bar of tau with the appropriate constant, then these generating functions are exactly the discontinuities that I've introduced before. So we know this in closed form in terms of Kupo-Kammer symbols. But something very important is to notice that this group, gamma 1, 3, is not any group. It is deeply connected with to the geometry of local P2. So for example, we know that the moduli space of complex structures of the mirror can be identified with the quotient H over gamma 1, 3. Also the generating functions of Gromov-Witten invariants on local P2 have modular properties under the same group gamma 1, 3. Then if we apply the Fricke involution of H over gamma 1, 3 on the generating function of the Stokes constants, we can introduce these dual holomorphic functions that I denote by f star 0 and f infinity star. So just taking y to minus 1 over 3y. Then these dual generating functions are again holomorphic quantum modular functions with respect to the same congruent subgroup gamma 1, 3. Now, something interesting to notice is that, so if you recall that the generators of this group are these elements T and gamma 3 that I write in this slide, then the original generating functions f0 and f infinity have a non-trivial cocycle under gamma 3. And this can be written in terms of the Stokes constants at strong and weak coupling. Again, not the exchange of the information between the weak and the strong regimes. And instead, if we look at the Fricke duals, then the non-trivial cocycle is the one under the generator T. And in this case, the cocycles are written in terms of the same regime Stokes constants. So the Fricke involution here acts not just by exchanging the generators of the congruent subgroup, but also by exchanging the roles of the weak and strong coupling Stokes constants. And Okay, there is also work in progress on the understanding of the role played by the frequent involution more explicitly, because well, this is also being studied in the context of the geometry of the local P2 as it applies to the moduli space of complex structures. So finally, as promised, I'm gonna introduce the general notion of modular resurgence. So what we have done with Veronica is we have taken what are the essential features of these examples of the trace of local P2 and tried to characterize somehow a general mathematical paradigm that could fit many more examples. And so this brought us to the definition of modular resurgent series and modular resurgent structure. So if we take any Gevrey-1 asymptotic series phi of y with complex coefficients, then we say that this has a modular resurgent structure if two conditions are verified. So the first condition we would like to have is that the Borel transform is singular along a tower of singularities. So it is not important that this is a vertical tower. So we want an array of singular points that are distanced by the same constant A in C. And we want that the resurgent series at each of these singular points are trivial. So there must be no perturbative parts, but only these constant functions that we identify with the Stokes constants. This has been, if you want the trivial, and this has been an essential part of the construction on the trace of local P2 that allows, for example, to identify the generating functions of the Stokes constants with the discontinuities, etc. The Stokes, and maybe one comment I can make on this is that, this was one of the reasons to look at the logarithm of the spectral trace and not the spectral trace directly, because if we, if you had looked at the spectral trace without taking the log, then you would have seen perturbative series attached to each singular points along the tower. Even if this would all be the repetition of the same initial perturbative series you started with. And the arithmetic content of the Stokes constants would be combined together, repackaged into Stokes constants that are not easy to interpret in a number theoretic way as it is in after you take the logarithm. And then, so the second point is that we want the Stokes constants to be the coefficients of 2L functions. So one can always build a Dirichlet series out of these sequences of numbers, but we would like these numbers to actually define L functions. And so the conjectures we propose on this modular resurgent series so if you write those down, so if you just write down those series, those are Dirichlet series, right? So they don't need to be L functions. But so the condition is that those Dirichlet series need to satisfy an Euler product expansion. They need to be convergent on some right half plane, and there has to be an analytic continuation to the rest of the complex plane. So that's what defines them as L function, which is what we verify in the case of the trace of local P2, for example. Sorry? No, over the prime numbers, you know, yeah. Yeah, so I guess we're still trying to understand what's the best definition to actually capture what we want and also potentially prove this conjecture. So at the moment we haven't used it, so we haven't put it, but could be necessary at some point. And so the conjecture is that if F is if F is a Q series, where Q, we take it to be e to the 2 pi I y, defined on the upper half plane, and we take the asymptotic expansion as y goes to 0 on the upper half plane, then if this has a modular resurgent structure, we conjecture that it is a holomorphic quantum modular form for some subgroup of SL2Z. And we also conjecture that we can reconstruct this quantum modular form by taking the median resummation of the asymptotic expansion. So this is something I didn't tell you in this talk, but for example, this formula, we also have it for the two weak and strong coupling asymptotic expansions of the trace of local P2. And so we conjecture it in general. And so beyond the topological string example, we have a large class of examples that come from the theory of mass cusp forms. And so for this, we can prove the modular resurgence condition. We can prove also this conjecture here. So both the median resummation part and the quantum modularity property. And there's also further evidence in the literature on combinatorics and quantum invariance of knots in 3 manifolds, which is a bit sparse and spread. So we don't have another full example that satisfies everything beyond this that I've already described, but there are parts here and there in the literature. Okay, so I'm gonna quickly conclude. So let me first make a brief recap of what I've said. So the important points are that the resurgence of the spectral traces of toric CY trifolds have this universal structure of peacock patterns in the Borel plane and rational Stokes constants that are conjecturally related to enumerative invariance of the geometry. Now, the resurgence of the spectral trace of local P2 in particular has been solved exactly thanks to that factorized formula for the trace. And it displays this rich analytic number theoretic structure where we observe the interplay of the Q series and the L functions that are built out of the Stokes constants in the two regimes. And we define this strong, weak, resurgent symmetry. And then thanks to these results, we try to propose a generic paradigm that links the resurgent properties of Q series with the analytic properties of L functions and quantum modular forms. And this is the heart of the modular resurgent structure story. And also want to say that L function, the functional equation connecting the L functions at weak and strong coupling that I described in the case of the trace of local P2 also plays a central role in the general story of modular resurgence. Even if I didn't enter into the details of this, I think Veronica also talked about this more specifically last week. And so open problems, well, there are many. First of all, we would like to extend our results to other toric CY trifolds. There's an initial numerical approach to local P1 times P1, but it's very hard to say much without getting more information. And potentially also about higher order fermionic spectral traces. It would be important to explore the geometric and physical interpretation of the Stokes constants. And there are different ways of approaching this. And importantly, we would like to translate our results in terms of topological strings quantities more directly. So as I described this story, starting from the topological string and the TSST correspondence, you know there is an indirect way of tracing this structure back to the topological string, but there's work to be done in understanding what this means and making it more precise. And also connecting with physical dualities, because of course there is a note of S duality in the story I have described as well. And finally, we would like to broaden the supporting basis for this paradigm of modular resurgence, having more examples, understanding better what would be the proper characterization of these modular resurgent structures, and the role of the L functions and their functional equation. And I'll stop here. So thank you very much. So yes, so that's why we like the conjecture. We just assume this peacock pattern with multiple towers. But for the first trace of both local P2 and local F0, we observed a single tower. When we look already at the second trace, for example, numerically, Marcos, Marinho, and Jigu have observed 2 towers in the case of local P2 and local F0. And so generically, yes, there'll be more towers, and it's not yet very clear how to generalize the arithmetic side of this story to multiple towers. Also, the modular resurgent structure, as I have given the definition, assumes 1 single tower. I don't think so, no. I mean, we know that it depends on the geometry, but I think first of all, there is not much evidence. So it would really be important to have more examples to understand this dependence. Yeah, well, so I guess in the yes, here. So, and I guess the definition of the total ground potential that enters the topological string spectral theory correspondence, if you want, you can realize the 2 terms as coming from the refined theory and taking the 2 specializations in the 2 limits that give you the standard and Nekrasov-Shatashvili total free energies. However, in the TSST correspondence in general, there is no, like the fully refined theory doesn't enter in its own. Like you only have the 2 specializations that enter the conjecture. Yeah, well, I don't need the correspondence to do everything I told you. So I introduced it because it's a motivation for me to look into these traces. But I could start with the Calabi-Yau and take the mirror curve, quantize it, and build the traces, and I would have everything I need. But then I don't, I guess I don't really know how to. Yeah. Yeah, it's a good point. I should think about it. Mm-hmm. That's something I haven't thought about. So I guess it didn't naturally appear in the story, but one could think about it and definitely ask the question if they play some role. So thank you. Sorry, which condition? Mm-hmm. Maybe yes, even if it's not very clear to me, because a lot of the ingredients in this diagram, a lot of the arrows, if you want, really work because of this. Which is why we also put that condition in the definition of modular resurgent structure in general. So I don't know if there is a way to circumvent that. Yeah, for example, the fact that you can, like the fact that, well, you can always think about the Dirichlet series of the Stokes constants, right? And ask if this is an L function, etc. But the role it plays in the story, how it connects with the perturbative coefficients on one side and with the discontinuity on the other side, those relations really happen because you don't have perturbative parts